In this video, we're going to take a look at the normal distribution. The normal distribution is a probability distribution that is widely used in statistics, probability theory, and other fields that deal with continuous data, unlike the binomial distribution, which deals primarily with discrete data. The normal distribution is characterized by its bell-shaped curve, which is symmetrical around the mean. The mean, median, and mode of a normal distribution are all equal. The standard deviation of the distribution determines the spread of the curve, with wider curves having larger standard deviations. Many natural phenomena, such as height, weights, and IT scores, are normally distributed. Here is a list of 10 that are normally distributed: the heights of adult humans, weights of newborn babies, IQ scores, blood pressure readings, scores on standardized tests, body temperature readings, time it takes to complete a task, annual income levels, amount of rainfall in a region, and the length of a particular species of fish. The normal distribution has many characteristics. It is a bell-shaped curve. It is symmetrical around the mean. This means that 50% of all data is above the mean, 50% of all data is below the mean. It is commonly associated with the 68, 95, 99.7% rule, or the empirical rule, which you can see on the diagram. 68% of all data is within one standard deviation above or below the mean. 95% of all data is within two standard deviations above or below the mean. 99.7% of all data is between three standard deviations above or below the mean. The area below the curve accounts for all probabilities. That is, that it is equal to 1. It goes off to infinity in both directions. What this means is that underneath the curve, in extreme circumstances, the probabilities get smaller and smaller and smaller the further you get away from the mean.
In this example, we have some normally distributed data. It has a mean of 60 and a standard deviation of 5. Using the empirical law, we can show that between 55 and 60, there is 34% of the data. Between 65 and 70, there is 13.5% of the data. Between 70 and 75, there are 2.35% of the data. Above a score of 75, there is only 0.15% of the data. So below 75, which is all this, would be 99.85% of the data. There is 13.5% of data between 50 and 55. Between 50 and 65, there is 68 plus the 13.5, which makes 81.5% of the data.
Just as with binomial distribution, normal distribution has its own special notation. If a variable x is normally distributed, you write the random variable x is distributed. You put a capital N to show that it's a normal distribution, and then the two parameters you show are the mean and the variance. Show that it is sigma squared. So you have to be very careful in some instances. If it is written like this, x belongs to n, and you are given, say, the mean is 10, and you're given 25, the 25 is the variance. If it is given in this way, x belongs to n, again the mean is 10, and you are given 5 squared, you know that in this case the 5 is the standard deviation. Here is a typical normal distribution question that you might get. It's quite long, it has 6 parts, but we'll go through each part individually. Whenever you're doing a normal distribution question, always draw yourself a diagram and mark on it all the relevant information. This will make it a lot easier for you to answer the question that you've been asked. So, the average weights of males in the UK are normally distributed, with an average weight of 84.27 kilograms and a standard deviation of 12.43 kilograms. Find A. The probability a randomly selected male weighs more than 93.5 kilograms. I've drawn my bell curve, and now I'll write in the relevant information. I know that my mean is 84.27. I know that my standard deviation is 12.43. And I want the probability a selected male weighs more than 93.5. Well, I know that 93.5 is up here. So I want that probability there. And I'm going to do this on a TI Nspire. And for the first one, I will show you exactly how to do it using your TI Nspire. I've opened the TI Nspire at a calculator page. So I go to Menu, 5 Probability, 5 Distributions, and the normal, because it happens so often, is right at the top, and there are 2 to choose from. We always use normal CDF because it is continuous data and not discrete data. In the IB, we will always use normal CDF, and then if we have to go the other way, we will use inverse normal. So we want 2 normal CDF, and here is our data. We want above 93.5, so our lower bound is 93.5. Our upper bound is infinity, because remember it goes on forever, but you can't put infinity in, so I just put a very, very, very large number. I know what my mean is. My mean is 84.27. And I know what my standard deviation is. It is 12.43. So that's all my information. If I press OK, I will get the probability that a man weighs more than 93.5 is 0.228874, which is 22.9% as of 3 significant figures. B. The probability a randomly selected male weighs less than 66.75 kilograms. So I'll start by drawing my diagram. So I know that the mean is 84.27. I know that the standard deviation is equal to 12.43, and I want a weight less than 66.75. Well, 66.75 is below the mean, so it's around here. So 66.75, and the area I want is here. So when I put it into the calculator, my upper bound will be 66.75 and my lower bound will be a very small number. So I put in a very small number for 66.75. I can't put negative infinity, but I put a very small number. When I've done it on the calculator, I get the probability that x is less than 66.75 is equal to 7.93%. Part C. The probability a randomly selected male weighs between 64.7 and 83.2 kilograms. So if I draw my diagram, if I put in my mean again, always do that. So that's 84.27, and my standard deviation is 12.43, and I want between 64.7, so that's somewhere down here, and 83.2, so 83.2 is just below the mean, so I want this area here. So my lower bound is 64.7 and my upper bound is 83.2 when I put it into my TI Nspire. So the probability that x is between 64.7 less than x less than 83.2 is equal to 40.8%. Before we go any further, I'd just like to point out one anomaly when dealing with normal distribution. The probability that x is greater than, say, 70 is equal to the probability that x is greater than or equal to 70. It doesn't matter, or it has no effect, whether 70 is included or not included. Because this is continuous data and using normal distribution, we cannot distinguish individual amounts. It is continuous data. The probability that x is greater than 70 is equal to the probability that x is greater than or equal to 70. Part D. The value of x if 8% of males weigh less than x. In this case, we have been given a percentage, so we know that 8% of our males weigh less than a specific value x, and we need to find this value. So our diagram will look like this. We put our mean in again, which is 84.27. Our standard deviation is still 12.43, but we are told that 8%, so this area here, 8% are below this value x, and we need to find this value x. So this is when we use inverse normal distribution. So I'll show you this one on the calculator. I've opened the TI Inspire at calculator page, so I go to menu. I want 5 probability. I want 5 probability distributions. This time we're going to use inverse normal because we're given an area and we want to know what value gives us that area. So 3. We know that our area is equal to 8% as a decimal, that is 0.08. We know that our mean is 84.27. We know that our standard deviation is 12.43. So in this case, a weight of 66.8 kilograms means that 8% of our males are below 66.8 kilograms. So for D, X is equal to 66.8 kilograms. E, the value of Y if 3.5% of males weigh more than Y. So if I draw all my information here for E, I know that the mean is 84.27. I know the standard deviation is 12.43. And I want the value Y that gives me this area of 3.5%. The probability that Y is greater than P is 3.5%. That means that the probability that Y is less than P is equal to 96.5%. My calculator cannot calculate this area here. It has to calculate this area here. So when I'm using my calculator and using the inverse normal, my area is 96.5%, which is equal to 0.965. When I put that information into my TI Inspire, I get a value for Y that is equal to 106.8 kilograms. That means a weight of 106.8 kilograms gives me 3.5% of the population above that weight of 106.8 kilograms. Part E. There are 107,979 males in Rochdale. How many are above the weight of 107.75 kilograms? So to answer this, I need to find the probability that X is greater than 107.75. And if I do that on the calculator, I get the answer 3.2%. That means I need to find 3.2% of 107,979. So I've got to do 107,979 times 32 over 1,000, which equals 3,455. So there are 3,455 males in Rochdale above the weight of 107.75 kilograms. Here is a typical exam question. Question 2. The height of the average female giraffe from a population where the heights follow a normal distribution is 4.57 meters and has a standard deviation of 1.28 meters. Find part 1, Q1, part 2, Q3, part 3, the interquartile range. Well, we know that Q1 is 25%. We know that Q3 is 75%, and we know that the interquartile range is Q3 minus Q1. Let's draw a diagram of exactly what we have. We are told that the mean is 4.57, so that goes there. We're told that the standard deviation is 1.28, and we want to find Q3, so this percentage is 25% in there, and this percentage here, which is Q1 below it, is also 25%. So therefore we're going to use inverse normal on both of them. So we want the inverse normal, where we have an area of 0.25, we have a mean of 4.57 and a standard deviation of 1.28. If we use our calculator for inverse normal, we get a value of 3.7066. For part 2, we want to use the inverse normal, but this time the area, because remember we can only do the area up to that value Q3, so it's 75%, 0.75. Again, it is 4.57 for the mean and 1.28 for the standard deviation. If we use our calculator, we get a value equal to 5.4333. For part 3, we want the interquartile range, which is equal to Q3 minus Q1, which is equal to 5.4323 minus 3.7066, which is equal to 1.73 to 3 significant figures. Part B. Between what two values do the middle 68% of the giraffe's heights lie? Well, if we draw ourselves a diagram, if we put on our important information, we know that the mean height is 4.57 meters. We know that the standard deviation is equal to 1.28 meters. Now, if we show our area, we want a value there we'll call X. We want a value there we'll call Y. And we want that to be 68%. Well, that is one of our important numbers in the empirical formula. We know that 68% of the data lies between one standard deviation above and one standard deviation below. So one standard deviation above, we can add 1.28 meters. One standard deviation below, we can subtract 1.28 meters. Therefore, X is equal to 4.57 minus 1.28, which is equal to 3.29 meters, and Y is equal to 4.57 plus 1.28 meters, which is equal to 5.85 meters.